fourth and last transformation we have, it's from D to A. So once again we want to do a heat exchange, but this time with the cold source, and in that case we use a heat exchanger, and once again we have two things we need to consider for a heat exchanger. The first thing is that we can consider it as isobaric, and second thing, we need the temperature difference with the other fluids with which it is exchanging heat, and in our case it's with the cold source. So here we can add a heat exchanger, and on the other side it will be the cold source, and this time we want the cold source to give heat to the working fluid. So in order this to happen, we need the cold source to be at a higher temperature than the working fluid. That means that we need to define here another temperature. So the one before here we can call it T-cons, like condensation, and this one would be T-evap, like evaporation, because the working fluid will evaporate in this heat exchanger, because it starts two-phase and it finishes in A as a complete vapor. So the pressure at which this heat exchange takes place is also a lower pressure than the pressure corresponding to saturation, to the saturation temperature of the cold source. And so we need to move from the Carnot cycle, which was at the same temperature than the cold source, from D to A, to a lower temperature. So here, once again, the heat exchange is isobaric, and the temperature at which it is done, so T evap, needs to be necessarily lower than the cold source temperature. D is already two-phase, but mostly liquid. A is somewhere there, but completely vapor. So what will happen? The fluid will just finish evaporating until it's completely vapor. For this reason, this heat exchanger is always called an evaporator. And now we have all the different components of vapor compression refrigeration cycle.